can do A, I think.
And keep in mind, the rational root theorem we'll come back to, and I do want to eventually have you work toward a proof of that too. But to the extent possible, we do want to give you like reasoning about why things are working in this course. That's what math is about. Because that's the problem you said you didn't have. 51 you said you didn't have, which requires. Okay. All right. So here's why. You don't need to take notes on this necessarily. I just want to make sure for those who are like, wait, Descartes seems like magic. Why does that work? I want to see. This is not a proof. In fact, you're welcome to look up the proof if you like, somewhere online, and you'll find that it's like pages and pages. And I feel like it's just not worth the effort. It's like not beautiful. It's not illuminating, even though it's all true. Okay. But this, I feel like, even though it's not a proof, will at least help you begin to see what the reasoning is behind it. Okay, I'm ready to hear your answers. Oh, you don't write it?
No, I'm writing down. I'm making sure.
Are you watching it?
Okay.
Can we get a little drum roll?
4. Oh, sorry, x minus 4. Right?
Okay, or you're factoring. Okay.
Well, can I just give like the sum?
Give the roots.
4 and 4 plus, sorry, if I simplify, so 2 plus root 3 and 2 minus root 3.
The crowd goes wild. Yeah, I'll give you your homework. That too. All right, sorry, where was I? Okay. So let's start with 2, just f of x equals 2. Certainly, there are no sign changes in f of x equals 2. Again, you don't need to write this down. I just want to try and explain why Descartes works. Okay, so don't be like, wait, okay, I'm going to make sure I draw that picture. You don't have to if you don't want. All right, so f of x equals 2 is very trivial. It's just a constant function. Clearly, there are no zeros at all. And as I draw these pictures, notice I'm only concentrating for right now on the positive side, right? The positive x-axis, whether or not these functions cross the positive x-axis. So the first bullet point of Descartes' rule of signs, right? Okay, so that's all we're looking for is, does this or does this not cross the positive x-axis? If we add a 3x to the mix, notice that this will not cross the positive x-axis, am I right? And also notice that there are no sign changes in this function. Now let's make things get crazy here. Let's add one more term, 5x squared, say. Now if it's a positive 5x squared, then notice that because of what we know about quadratics and the end behavior, that this is going to turn up. Still, no chance for this, if there are all positive number coefficients here, for this to touch the x-axis on the positive side. So in the case here, we're only working, again, this is just intuition. This is just an example with numbers. We have here, though, that this has no sign changes. And we also can observe that there will not be any positive real zeros. Well, what if instead we had added a negative 5x squared instead here? Ah, ooh, they say. Yes, I know. Well, then we know that because of the end behavior, because of what we know about parabolas, this is going to go down, and there is going to be 1 on the positive side. 1 real 0 on the positive x-axis. And notice that there's 1 sign change as well, right? You can see that that's happening. Okay, let's go all the way back up to the root of the tree here. What if at the very beginning we'd add negative 3x instead? Oh, okay. Well, then we have this graph. And does it cross the positive x-axis? Yes, it does. And notice that there is 1 sign change. Right? Now, what if now we add 5x squared to the front of this? Well, we have now a parabola that, again, end behavior tells us it's going to go up on the right eventually. So it either looks like this or this. We're not sure. Right? We know that by adding a 5x squared to the front of this, it's either going to do this or it's going to do this. But we do know one way or the other, it is eventually going to go up. Do you agree? Just because it's a positive leading coefficient and all that. All right, so what does that tell us? Well, that means there are either 2 zeros in this situation or 0 positive real zeros, right? Or it could be a double root, but we'll count that as a double root. It's 2 for the count, right? 2 sign changes. Notice. Do you see why this is kind of working? And then the last case would be, what if we had added a negative 5x squared to the front of this, and you get this kind of picture, similar to earlier, and we have 1 sign change again, yielding 1 positive real solution. So does this make sense a little bit? Again, this is not a proof, but at least it helps you understand that this is not like magic why this works. It kind of makes sense that it should work. I have this, but I don't want to belabor it. Oh yeah, go ahead, Dave.
So you can have a graph that like the one side of the axis of symmetry is like the y-axis, and so one is on one side, one is on.
These are very, very inaccurate pictures, just to be clear. So yeah, so with that in mind, say what you said again.
Yeah, so like, but you can also have like a graph where the axis of symmetry is such that like one of the x-intercepts is the negative and one's on the
Right. In fact, that's how these are. In fact, these guys here, the other x-intercept is on the negative side of the x-intercept.
And then that would reflect a degree f of negative x with a negative.
Right, yeah, and we get that one from that. Yeah, this is an analysis only on the right side of the function. In all of these, I only graph the right side. So repeat all of this for the second bullet point of Descartes, thinking about the negative side. Yeah. I should say, I'll put this up here, but someone might, this is mainly just to hear someone out who might say, well, what if we started with -2? You didn't do that. Okay, here you go. You get the same tree, though.
Oh, beautiful tree.
Okay, there you go. All right. I mean, it's different places here, but basically the same analysis. Okay. So does that, I don't know if that helps a little bit illuminate Descartes. Again, not a proof, but just interesting. I do want to just remind you that with great power comes great, difficulty in factoring the polynomial. Meme day yesterday, this could have been you yesterday doing the memes. Okay. All right. Well, the discussion today moves in the direction of complex numbers. So, really the lesson in a nutshell is, last night you factored a lot and stopped, if necessary, before getting to before getting to non-real factoring, right? So, tonight we would like to keep going, that's all. There you go, that's the lesson. No. And we can say a little more. We can finally say what the fundamental theorem of algebra is, provided that we have in view complex numbers, because this doesn't really work unless you have complex numbers. It's a theorem that I think most of you have heard, or if you haven't heard it, at least you felt it in your heart, even if you haven't heard it. If you come to a 5th degree polynomial, you kind of come to it with the expectation that there will be maybe 5 zeros, right? You have that feeling. Up to multiplicity, right? Some of them might be repeated zeros, like it says here in the second sentence. But the key word here that makes today, this thing we have to say in today's lesson, is complex zeros. Right? We understand that a 5th degree polynomial doesn't necessarily cross the x-axis 5 times, that's for sure. Even up to multiplicity, that's not true. So, and by the way, I should say, after having made such a great point of the fact that we're always going to try to the best of our ability prove everything that we can in this course, because that's what math is: argumentation, reasoning, logic. Unfortunately, this is a statement, though seemingly simple, is very difficult to prove. In fact, it takes. I think that it's not appropriate for high school students or college students. It's that hard. Yeah. It takes like a lot of abstract algebra to prove this statement. But it's an easy sell, though, isn't it? I mean, because we all kind of already feel that it's true. So I think we can move on because the intuition's there. But this is a very difficult thing to prove, even though you might think that it shouldn't have to be that hard to prove. Yeah.
So like if it's degree 5, it has 5 complex zeros.
Yeah, that's degree 5. It has 5 complex zeros, some of which may be repeated. All right, well, if you grant that this is true, this is just an immediate consequence, and it comes from the factor theorem from yesterday, right? If z1 is a 0, well then of course x minus z1 is a factor. So what that means then is that every polynomial can be factored in this way, right? Some number times x minus the 0 times x minus the 0, n times, where n is the degree of the polynomial, right? By the way, we often start using z's sometimes when we talk about complex numbers. It's just tradition, I don't know why. Another result, this is kind of a nice summary of results that maybe you have known and thought about before. I don't know if these are not, none of these is a huge surprise to you, I don't think. Is the complex conjugate zeros. And so someone say before I say it, look at theorem, will say. Do you remember what a complex conjugate is?
Oh my goodness.
You want to take it, Reggie? You got you tie in the wings if you.
So like, it's like let's say you have like a denominator, like a fraction, right? You have like 1 plus the square root of the square root of 5, right?
Well, but I want to think about complex numbers here.
It's like, actually, never mind that.
Small model, yeah, go ahead.
I think we did this last year, but I'm not sure if I'm right. I think we're not allowed to have complex numbers in the denominator.
Well, there are not going to be any fractions here today.
No fractions, okay.
Not yet, not in our lives yet. Yes, Henry. Can you say it just one more time? Okay. How about I just tell you? Have you heard of complex conjugates? So a complex conjugate is if you have a number like 2 plus 3i, 2 plus 3i, what's the conjugate? 2 minus 3i, right? Okay, that's all. That's all.
Oh, yeah, that.
So you're overthinking it, maybe. I don't know. All right, so that's what this says. And furthermore, that if one is a 0, then the other is 2. Right? Provided that the coefficients of the polynomial are real numbers. Which is usually, that's the only thing we'll ever consider in this class. But all I'm saying is that all bets are off if you tell me that your polynomial is like 2ix squared minus x plus I or something, you know. No, we're not going to do that. All I'm just saying is like all bet, only if this only works. Does this have complex zeros that come in conjugate pairs? No. No, it does not. I just wanted to make sure that you understand the context in which this makes sense. Only with real coefficients. But if that's true, then we have this result. It's nice, because if you know one 0, you know another one for free. You ready to do some more factoring? Yeah, we should. It's good for us.
Factoring is not for the soul.
I have another wonderful 5th degree polynomial for us to just go into. See if we can make it fall. You're excited to Yeah.
Okay.
Okay. But is he tiring?
Are you ready?
I did put these online.
All right.
Oh, you did? Oh, yeah, I'll check that.
Yesterday, the day before. Okay, let's do it. Here we go. 5th degree polynomial. I like 5th degree. That's good. We keep giving you 5th degree ones. Well, 3rd degree is kind of too easy. 4th degree would probably be easy.
Yeah.
5th degree is good. 6th degree is kind of, as the kids say these days, extra. Like 6th degree, right? We get the point if we do a 5th degree one. It's good. Nice challenge right in between. Okay. So give it a try.
I would like to attempt a 5th degree polynomial. You're cut off or canceled. Something like a friendship.
All right, let's crowdsource this a little bit. Anyone have success with a root yet? What are the? Did 1 work?
Wait, so do we just like?
What are you trying even?
Subtract division. I'm using the plus.
You have plug in a bunch of factors of 8. See which ones work. 1 works. Someone said already. Wonderful.
Oh,
It wasn't that nice. Wasn't that nice of us? 1 is actually pretty easy to check.
Huh?
I'm glad we got that on the tape. That's good. Okay. Yeah, so 1 works, someone guarantees me. Okay. Yeah, I don't know. We'll see. We'll see. The tape here is all. No one is safe. Okay. All right, good. Let's summarize where we are each time. You don't have to do this, but I think it's helpful for me at least to see like what progress have we made. X minus 1 times where are we at? X to the 4th minus 2, x cubed minus 7, x squared minus 2, x minus 8. Okay, good. We're chipping away at this thing. Now we've got a quartic in our lives. Can we make another good guess here? Does 1 work again? Anyone have a? Does 2 work? -1? By the way, -1 doesn't work. 1 doesn't work. Okay.
So let's try it.
Let's try 2. Can you try? Just tell me. Give a holler if one of these works. -2 works? All right. Let's see. I hear word on the street is that -2 works.
We're on the street.
If you believe, Joy.
Oh my god, it worked. I did it. I take back
Wait,
the
you did?
I take back the from like
It's too late.
a minute ago.
It's too late.
I got it though. Now
See,
I
if everyone
get
just
it.
kind
I
of
saw
calms
it.
down a little bit, you
I
know.
understand now. I've grown as a person. Yes, I have.
Let's not get carried away, Utah.
It works. Just do it again.
Just do it again.
Just keep on doing it.
Yes.
One thing to notice here is that plus and minus 8 are now off our list of things to try even. Yeah.
Wait, 1 plus or minus 8?
Yes.
The 2 like large.
Also notice that according to Descartes, there will only be positive roots of this now. You see that? Because the sign changes. If you plug in -x, it's all negative coefficients. If you plug in -x, right? So it's not worth trying plus or minus 8, that's for sure. It might be worth trying 4, but it's not worth trying -4. But maybe it's already obvious why x minus 4 is a factor of that. Is it obvious that x minus 4 is a factor of this?
Yeah.
Grouping.
Grouping, someone says. Do you remember factoring?
Oh my god, did you say grouping?
Do you remember factoring by grouping?
Yes.
You could just maybe factor this by grouping too. So what remains? X squared plus 1. Okay.
That's not good.
Yeah, so we'll keep going with that though. Good. Good. So feel free to do that over here. You'll get the same result if you divide out 2 here. Oh, did I say 2? 4. That's what I meant. 4. So you can try it too if you want. But you'll get this result. X squared plus 0x plus 1. All right, but then it did say in terms of linear factors, right? According to the linear factorization theorem, we should be able to get it a factorization in terms of all linear factors. And right now we still have a quadratic factor. So what is that factorization, someone? Yep, see we're in the world of complex numbers here.
Good old
Yeah, x plus I, x minus I.
Like it's I times I.
And if you're not sure what those two things are, well, just solve the quadratic. X squared plus 1 equals 0 under what circumstances? Yes, right? I mean, if you're not sure what to put here, just go ahead and solve the quadratic and then do x minus 1 of the zeros of the quadratic and then x minus the other 0 of the quadratic. Okay. All right. Any other thoughts there? In the box is the answer. Are you okay with that? That's the linear factorization we're looking for. Listen, please.
Wait, I'm just clarifying. I squared is -1, right?
I squared is -1. That's correct.
So I squared is 7.
I squared is -1. Yes. Yes.
I squared is negative.
So what's I squared ever get?
Negative.
Negative. All right. Good. We got that cleared up. Now, on the next slide, I think we're going to, just for the sake of time, we're going to skip this slide. But I do want you to at least look at the problem and verify that this is something that would be really interesting to do. Do you agree? Wouldn't that be fun?
Very interesting.
It does work. I promise it divides evenly into it. You could do the work and you'd find yourself having a great deal of fun.
A great deal of fun.
Yeah.
So like if we were to divide, how would we divide something like division when the divisor, the smaller number is not just 1?
Yeah, I guess I should have said x minus 1 minus 2i.
Wait, what is that?
I'm just saying this is the thing that divides into this. Yeah, so the thing we're plugging in up in the corner is 1 minus 2i. So we won't do that, but I just want to just let you know that synthetic division still works if you want to do that. Yeah.
Would we get a problem like that on like a quiz or a unit test?
I don't see why it's a problem for you to get one like that. But yeah.
Wait, so if we were to say So we have like 2i and like negative I.
Huh?
Like how would we define this?
You just do 1 minus 2i up in the corner. And then 4, 17, 4, 0, 17, 14, 65. Start multiplying.
1 minus 2i. Oh,
All right, let's highlight this right now. This is, I think, worth talking about. So multiply this out, and the reason I still have, well, I mean, there's lots of reasons maybe to write it this way, but one reason is I'd like you to maybe think about it as you're multiplying out, even though it's technically, I guess, 2 trinomials, I'd like you to think about it as if it's 2 binomials. That might help structure your work as you multiply these. You can do it any way you like, as long as you do it correctly, I don't care, but I think that's the most helpful way to do it. We're going to make a point with this, that's why I'm doing this. Notice that it's a nice setup here. 1 plus 3i and 1 minus 3i. Something is clearly a plus. Or maybe you're wrong, but you're still not stupid. That seems very disparaging. Even if you're wrong, maybe it's not the case. You could just do it, actually, too.
I did it. That's like quadratic. Yeah, x squared.
I guess I meant do it correctly. You know, do it.
Oh, so x squared. X squared plus 100. Am I stupid? Because 1 plus 3 and 1 minus 3 is just 10. So x minus 10.
I know how to foil, everybody.
Wait, x minus 3.
Do you agree that that's me foiling?
X squared.
Right?
No, x squared minus 28 plus 100. No.
Calm down, Jay. Calm down. All right. So what happens in the middle? Yeah. What cancels out? Yeah, the 3ix and the negative 3ix will cancel out if you go to multiply these out, right? Just in the middle here. So what are we left with just in the middle? What's this? What's left in the middle here? Negative 1x. And there's another negative 1x. And there will also be a negative 3ix and a positive 3ix. So what's left in just the middle piece here?
x squared minus
Right? And then on the end, what's that? That's the difference of squares. Yeah, so what will that be? It'll be 1 minus 9i squared. I forget what I squared is, though. That's right. So it's 1 plus 9, which is 10, is what that little product at the end comes out. Well, I just want to make sure we highlight this, because this is something that in general happens with x minus a number and x minus its conjugate, okay? Let's come back to ordinance. So I have it generally worked out just to show you that the thing that just happened is not a fluke. This is in fact always what happens. If you work it out with a's and b's, you see that that is in fact always what we get. We always get twice a as the coefficient in the middle here. We always get over here a squared plus b squared, okay? You don't need to memorize that. I think if you do it enough, you'll just feel quick, you'll get quick at that. You'll feel it in your heart. And this kind of quadratic that has 2 complex conjugate roots is called an irreducible quadratic. Or it says here, irreducible real. That is, if you were to factor it, you would have to use non-real numbers. Now, there's no such thing as an irreducible cubic. Why? There's always one real 0 at least for a cubic. So if you have a cubic, you should definitely be able to factor it as x minus something real times possibly an irreducible quadratic, maybe. Same with a 4th degree or any higher. So there's no such thing as an irreducible other higher polynomial. Okay. So I just want to make sure you're clear that sometimes, like even on the last one, when we have x squared plus 1, technically that is probably the very simplest example of an irreducible quadratic. X squared plus 1 would be the simplest case. But this is an irreducible quadratic too. Okay? So if it says in the instructions to factor using linear factors, do the thing we first did. Go all the way to x minus, x minus, x minus, right? If it says factor with linear factors and irreducible quadratic factors, it just means stop the step before that where you have quadratics. But you shouldn't be stopping with cubics, that's for sure. So that's what this says here. So the homework tonight will have sometimes varied instructions, right? It'll have both of those instructions. Homework 4 is what we're doing tonight. I think that's a good place to stop. It's the same kind of thing. Guys, let me see all your blood, sweat, and tears on the homework tomorrow, okay? I want to see all that good work. Factor, okay?
I'm so excited.
Yeah. It's good for you. We're heading to the gym tonight, okay? If we do this, so these two, if we do this, produce for us two real form, right? Two irreducible quadratics. So you'll never have Have a great day. Bye, you guys.
Bye, thank you, Mr. Chase.
Have a nice day.
Thank you, Mr. Chase.
See you soon.
Thank you.
Thank you, Aiden.
I put up the homework, the workout there.
Bye, everyone.